Okay, so in the last class, we had looked at some major historical developments in radiology. And we talked about a better X-ray tube with the invention of the Coolidge tube. We talked about the image intensifier and how it greatly reduced patient dose in fluoroscopy. We talked about our Bucky mechanism with the Potter-Bucky diaphragm. Well, we're going to start today by looking at the developments that occurred in image receptors. Now, when Röntgen first discovered X-rays and realized their potential importance to medicine, the images that were recorded in those early days were on glass plates. But shortly thereafter, 1896, Pupin discovered or invented, he just invented, he didn't discover, screen cassettes. And what he did was sandwich photographic film that is sensitive to light between two fluorescent screens that, when they were struck by X-rays, emitted light. Now, the utilization of screens was huge because it allowed a much smaller amount of radiation to be used in order to create an image. In fact, the utilization of screens decreased patient dose by a factor of 50. So that was huge in terms of dose reduction to the patient, which at this time they weren't really even concerned with because they didn't realize the potential for biological effects. But when you think about this discovery or this invention, one of the things that's amazing to me is that the actual phosphor material that was utilized, which was calcium tungstate, was discovered by Edison. And in order to come up with this efficient compound, he actually tested more than 5,000 chemical compounds to find one that was efficient. And it had to be efficient at absorbing radiation, and it had to be efficient at converting the radiation that it absorbed into visible light, because the visible light is actually what exposed the film. So again, consider that time frame, the late 1800s, and he's testing over 5,000 chemical combinations to come up with calcium tungstate. And it truly is remarkable that calcium tungstate screens were utilized for 80 years or so. When I came into the profession in the late 1970s, calcium tungstate screens had just been replaced by a better type of screen. So this development was huge in imaging in order to reduce patient dose. And again, it lasted, or it was utilized for many, many years. Now, as we hit the 1960s, this was the time frame that we started to see different modalities develop, or different ways to create images. In 1966, sonography, which is ultrasound, was invented, and we all know that we now use ultrasound to visualize many areas of the body. Most people, when they think of sonography, think of babies, but there are so many other areas that sonography is utilized. Now, in the 1970s, this is the time frame when that original calcium tungstate compound was replaced. In the 1970s, the rare earth compounds were developed. And the rare earth compounds were gadolinium oxysulfide, yttrium oxysulfide, lanthanum oxysulfide. These compounds were more efficient at absorbing the radiation and converting it to light. And again, the light is what ultimately exposes your film. Because they were more efficient, they allowed us also to use less exposure. So the conversion from calcium tungstate screens to rare earth compounds reduced patient exposure further by a factor of 2. Also in the 70s, this was when we first started to see the conversion to some digital imaging formats. Computers were gaining speed and gaining power. And so the first computer processing of an image occurred in the 1970s with computed radiography. And computed radiography didn't really hit the market until much later, but that was the early days. Also in the 1970s, CT was becoming widely distributed as a modality. It was actually invented in the late 60s. MRI was actually invented in the 70s and became widely distributed as a modality in the 1980s. So as these new modalities developed, it usually was like a 10-year time frame from their initial development to broad or widespread clinical use. So digital imaging. Everything that you're using today is digital imaging. And digital imaging has been around a long time now, since really the 1970s was its earliest time frame. But it took a long, long time before it became widespread in general diagnostic radiology. So if we look at the development of digital imaging, 1979 was when we first started digitizing medical imaging, and the first modality that went digital was really fluoroscopy, because in the fluoroscopy imaging chain, the image information was already being converted into an electronic signal, which is electricity or a voltage waveform. It was easier to take that electronic signal and to digitize it in fluoroscopy than to develop any other of the modalities. So digital fluoro has been around a long time and really was the first major general diagnostic area that went digital. Part of the problem with developing digital imaging was, what did you do with the images that you had? Initially, there was nowhere to store these images because PACS was not really introduced until the early 80s. You say, well, what is PACS? You may have looked at this in your introduction class. So PACS stands for Picture Archiving and Communication Systems. And the PACS systems store all of our digital images. So every radiology department has a PACS system, and they have actually redundant systems where the images are held in multiple places in case of disaster. And at that same time, when the PACS systems were being developed, came the concept of teleradiology. And teleradiology is where the facility that creates the digital images actually sends them somewhere else, typically for reading. For example, for many years, Emory Healthcare radiologists have read CT and MRI images from some clinics in Florida. Those images are sent to us securely, electronically transmitted. They're interpreted by our radiologists, and the reports are then sent back. Before the early 80s, that was not possible. Also in the early 80s, we mentioned that the basics for computed radiography or filmless radiography were coming about in the 1970s. But I think 1984 is the date that is stated for the actual full rollout of CR, or computed radiography. Computed radiography can also be called phosphor plate radiography, or referred to as the phosphor plate systems. These were the first systems that didn't use film. So in the early days, sometimes they were called filmless radiography. They use a photostimulable phosphor plate to capture the image. And the latent image is the image that we know is on our detector, but we can't see it yet. We have to process the image to make it manifest. So the manifest image we can see, the latent image we can't see. With the CR systems, our imaging plate was exposed as normal in any radiographic procedure. The plate was then taken to the plate reader, where it was scanned by a laser, and that released the latent image in the form of visible light. That visible light image was then converted into electric current. It was amplified, it was digitized, and then it was sent to the computer for processing and display. So the CR systems, or the phosphor plate systems, were the first digital systems that were used widely in radiology, in general radiology. The problem was at the time that we didn't really understand how the technology worked or how we should adjust our exposure factors. So in those early days, we actually overexposed a lot of patients. And that was the bad thing about these new phosphor plate systems, is that patient exposure basically doubled. Now we since have corrected the error of our ways, and so now not so much. It wasn't until about 10 years later that the DR systems came about, or the flat panel systems. The DR systems can be called direct capture or digital radiology. Initially, they were called cassetteless radiography because this was the first receptors where we did not have a cassette. The receptors are literally built in to your equipment assembly. Now we know that we have mobile DR systems, so the term cassetteless or cassette-based digital imaging, those have sort of gone away as technology has evolved. The DR systems today are typically called the flat panel systems. And you will learn all about the details of these systems in courses in the future. So for DR, with the DR or the flat panel systems, as soon as you take the exposure, you will see the image on your monitor. There's no taking a cassette across the room or into the control area or out into a general technologist work area and putting it in a processor. No processor or reader is required. It's done automatically. One thing that's important to know is that for digital imaging to develop, we had to wait on computer power. These systems would not have been possible until computers had the capability of dealing with these very large image files. DR came later than CR because DR also had to wait until we could build image receptors with very small detector elements. Because if you can't get a very small detector element, then you can't image very small structures within the body. So with the development of digital imaging, there's obviously advantages. The biggest advantage is post-processing. When I first came into the field, all of our images were on film. Once that film was exposed and processed, that was the end result. You couldn't change it. But with digital images, we have the ability to make adjustments. We can adjust the brightness, which is how light or how dark they are. We can adjust the scale of contrast so that we can see many shades of gray in their long scale, or fewer shades of gray, which is short scale. So we have the ability to change the image from its original appearance. With the advent of digital imaging, and because of the receptor characteristics, it has also dramatically reduced the number of repeat exposures that we use or that we do due to technical factors or exposure factors, because these are what we would call wide latitude systems. They will allow a lot of leeway in our selection of technical factors. They can create an image that looks acceptable even if it's underexposed or overexposed. So that's good. The digital systems have reduced the number of repeats, which ultimately reduces patient exposure. They've also, if they are used properly, reduced radiation dose to the patient and to the operators. With these new digital systems, we can increase our KVP and decrease our mass, which means we are imaging with a higher energy, higher quality beam and using less radiation, which is better for the patient. So it's reduced radiation dose. And ultimately, over time, it will reduce, these digital systems will reduce expense because the receptors are reusable. X-ray film was very expensive. One of the main ingredients in the emulsion on the film was silver. Well, we know silver is expensive, and they were not reusable. Once the film was developed, that was it. So film was very expensive. So over time, digital systems should reduce expense. They also, in terms of digital systems, increase our efficiency because they will allow us to do more patients in the same time frame. So patients can move through the hospital quicker, they can have radiographic procedures that go more quickly, and we can now convey our information to the radiologist and to any referring physicians more quickly. So all of these are advantages to digital imaging. Like everything else, there are some disadvantages. There is a slight loss of image resolution or detail with digital receptors, and there is a high upfront cost. So those would be considered disadvantages, but they are outweighed by the other multiple advantages. All right, so we have finished looking at sort of the evolution of equipment. So now we're going to talk about living with radiation. And I know that you talked about some of these things in intro, so hopefully this will refresh your memory. At this point, do any of you have any questions? Anybody have any questions? All right, well, if we have no questions, we'll just continue right on. Okay, so you have chosen an occupation where you're working with radiation. And when people hear the term radiation, that's kind of scary. So we're going to talk about a general definition, and we're going to talk about different types of radiation. So if somebody in your family says, you're working with radiation, what is it? Well, radiation generally is the transfer of energy through space. And there are different classifications of radiation. Radiation can be particles, they can be mechanical waves, or they can be electromagnetic waves. Now, your textbook uses these three classifications. I will just be honest, most other textbooks do not consider mechanical waves as radiation. When we think of mechanical waves, that's sound waves. And so definitely in imaging that relates to ultrasound. But in general, when we talk about just classifications of radiation, it's typically particles and electromagnetic waves. So those are the two that we're going to focus on. So when we think of particles, think of subatomic particles, protons, neutrons, electrons. Particles such as electrons can be given energy, and they have kinetic energy, so they would be considered particulate radiation. Alpha and beta particles are emitted from radioactive nuclei. Alpha particles are big. They consist of 2 protons and 2 neutrons. They are identical to a helium nucleus. Beta particles are identical to electrons, except they don't come from the orbital shells. They come from the nucleus during radioactive decay. So those are examples of particulate radiations. When we think about mechanical waves, again, not typically considered radiation by most other references, but your text, your author does. And we're looking at sound waves, mechanical pressure waves that are moving through space. Now for us, we are most concerned with electromagnetic waves, because electromagnetic waves are what X-rays are. And there's different kinds, and we'll talk about them just a little bit more in a moment, but visible light, X-rays, radio waves, infrared radiation, ultraviolet light, microwaves, all of these are examples of electromagnetic waves. So if we think about particulate radiation and mechanical waves, they have kinetic energy, which is the energy of motion. And we'll talk more about kinetic energy when we get to classical physics. But they have energy by virtue of their velocity. They are moving. If particles are moving, they are particulate radiation, and they can interact with the body and potentially cause harm. Electromagnetic waves consist of an electric field and a magnetic field, you see it diagrammed here, perpendicular to each other, moving through space together. So you have that fluctuation of the electrical and the magnetic fields, and they are pure energy. Electromagnetic waves have no mass. So if we had a very powerful microscope, an electron microscope, we could see particulate radiation because it has mass. But we will never be able to see electromagnetic radiation because it has no mass. It is simply a wave of pure energy. And like we said, there's many different types of electromagnetic radiation. And they are listed together in a table that we call the electromagnetic spectrum. If we look at the spectrum, at the low energy end, we have radio waves, then microwaves, then infrared or thermal radiation. Then we get to the visible light spectrum, then to ultraviolet, then at the top, X and gamma rays. X and gamma rays are identical except for point of origin. X-rays are man-made. We produce them in the X-ray tube. Gamma rays occur in radioactive decay. When radioactive atoms are trying to reach stability, they will emit from the nucleus particles such as alpha and beta, or pure energy, which is gamma radiation. So X and gamma are at the high energy end of the electromagnetic spectrum. Radio waves are at the low energy end, but all of these are electromagnetic radiations. Now we are concerned about ionizing radiations, and ionizing radiations are able to eject orbital electrons from atoms. And only X and gamma rays in the electromagnetic spectrum have the energy to cause ionization. A single X-ray photon can cause many, many ionizations in a patient's body. And we are concerned with that because as these electrons are ejected, they can change the properties of the atoms, and they can break chemical bonds. They can cause chemical bonds to occur that would normally not occur. So they cause disruption of atomic structure. And that disruption can ultimately cause harmful biological effects. So in general, ionizing radiations are radiations that have enough energy to eject orbital electrons. If we're referring to electromagnetic radiation, X and gamma radiation are ionizing. If we're referring to the particulate radiations, both alpha and beta are ionizing. So how are we exposed to radiation? Well, we are exposed to radiation all the time. We are exposed to environmental radiation, which is also called background radiation. It can also be referred to as natural background radiation, just terms that all mean the same thing. And there are three general types of environmental radiation: cosmic, terrestrial, and internal. And on the chart, if you look, we can see the breakdown. Now, cosmic radiation comes from outer space. The Earth is constantly bombarded with both electromagnetic and particulate radiation. The good news is particulate, well, not particulate, but all of the cosmic radiation is filtered by the atmosphere. So we do not receive all of the cosmic radiation that's targeting the Earth. A lot of it's filtered out before it ever gets to the Earth's surface. However, if you live at a higher altitude, you will receive more cosmic radiation than if you live at sea level. And we see that cosmic radiation accounts for about 5% of the radiation exposure to the US population. Then we have terrestrial radiation, and terrestrial radiation comes from the Earth. And there are naturally occurring radioactive materials in the Earth. There's three families. There's uranium, actinium, and thorium. And over time, these radioactive elements decay and they emit radiation. So if we look at terrestrial, we see 3% of exposure to the population is from terrestrial radiation. But that really is misleading because you see this very large area of radon and thoron. Radon gas and thoron gas account for 37% of natural background radiation. As those naturally occurring radioactive materials decay, The byproducts of that decay are radon and thoron, and these gases seep up through the earth and provide really the largest exposure from environmental radiation. The last type of environmental radiation is internal. And internal radiation comes from things that are naturally inside our body, such as potassium-40, or things that we ingest. Foods that we ingest may have trace elements of radioactivity. And internal radiation accounts for about 5% of the total exposure to the population. So if you add this up, what you see is that environmental or natural background radiation accounts for approximately 50% of the exposure to the US population. And remember, from the day we are born until the day we die, we are all exposed to natural background radiation. Then we look at man-made radiation, medical X-ray, nuclear medicine, the nuclear industry, consumer products. Well, they all account for the other 50%. And if we look at this, the largest piece of the pie is CT. CT accounts for 24% of exposure to the general population in the United States. Now, this data was published, I think, in 2006. Since that time, CT has made great strides in reducing dose. So I think it will be interesting to see what percentage it accounts for the next time the data is published. But if we look, we see nuclear medicine is 12%, interventional fluoroscopy is 7%, conventional radiography is 5%. So medical exposure in general accounts for about 48% of exposure to the population. We see consumer products here, and then industrial, and look, occupational. Occupational exposure to the general population is very low. Of course, the number of people working with radiation occupationally is also very low relative to the entire population. So we're all exposed to radiation all the time. Sources from the earth, from the sun, from the stars, those two are cosmic. Minerals in buildings, that would be considered terrestrial. If you live in a brick house compared to a wooden home, your background radiation would be higher because of clay in the bricks. Same is true for a stone house. And then again, we also have these natural radioactive sources within our bodies. Here's some sources of radiation you might not think about. Smoke detectors, the lantern mantles when you're camping, cigarettes, bananas, which have potassium-40, even your drinking water. But really the most serious or the greatest source of radiation is typically radon gas. And like I said, radon gas seeps up through the ground after radioactive decay occurs, and oftentimes is trapped in people's homes. And so that's where exposure occurs. Like I said, a lot of people are afraid of radiation, and with good reason. There have been some real and imagined radiation disasters. We know from history, Hiroshima and Nagasaki bombings in World War II were devastating. When we get to the radiation biology class, we'll learn a lot about that. Also, the Chernobyl nuclear power plant meltdown that occurred in 1986 released huge quantities of radioactivity. More recently, the tsunami and the meltdown of the Fukushima power plant in Japan also was a large-scale radiation disaster. And there have been many more over history. Most of them related to nuclear power or medical errors, not so much related to war, other than Hiroshima and Nagasaki. The 3 Mile Island incident that occurred in the United States in 1975, relatively speaking, did not emit enough radiation to really cause any amount of biological damage to the surrounding population. So it's considered, so it was a problem. They did have an issue, but in terms of biological effects, none really, or were expected, and none have been shown from that problem. So I know these two quotes are very long, and we know that you really shouldn't do that on PowerPoints, but I took them so that you could just have the full quote. But basically what you need to understand is when we think about medical imaging, every patient has to consent to an exam based on the risk versus the benefit of the exam. The risk of the radiation exposure versus the benefit of the diagnosis. In imaging, the benefit typically far outweighs the risk. We have much better equipment, much more sensitive receptors, so we are delivering a much lower dose than we ever have. As technologists, we all need to follow ALARA, which is as low as reasonably achievable. We need to do everything that we can to minimize patient dose. Remember, our objective with every exam is to produce the highest quality images with the lowest possible radiation dose. That being said, we do know that accidents and acts of war occurred that caused problems. In the early radiation workers, we also know that there was an increased incidence of leukemia and other cancers, incidence of erythema, which is skin reddening, radiodermatitis, those types of things, because in those very early days, they did not realize the potential for harm. But after that was realized in the early part of the 20th century, we've done tremendously better. We use proper shielding, proper distance. We limit our exposure. So actually the incidence of disease among radiographers is no different from the overall population. And in fact, in many areas, the health of radiographers and radiologists is better than the general population. So when you think about your profession and the radiation, should you be afraid of the radiation? The answer is, as long as you are following acceptable practices, the answer is no. You should not be afraid of the radiation. This is a very safe profession. There's really more risk in a 40-mile commute every day than there is in being a medical imaging professional. So it's not something that you should worry about. So that ends the information for